Okay, where's the picture? Okay, the chain rule, a big one, it's usually the biggest challenge of all the rules, because for the most part it is the composition is the actual challenge. Once you have the decomposition, like we did here, then it's really not that hard. So you just differentiate twice each of them, and then you multiply. The back substitution sometimes forgotten, but that's not really that's such a big deal, unless you continue with that solving a problem, and then you have an extra variable which will mess you up. So like I said, the composition, decomposing the function, usually where things get hard. So let's see. So the importance of the compositions, I think I've been emphasizing it, and everything consecutive computation is a composition. One is a very special kind of compositions is called the change of variables. It is describing a behavior that depends on, for example, the position depends on time. Okay, so and then what you might be doing is decide at some point that I'm gonna do, say, y is equal to f of t, and you're gonna resize the time. So in seconds. And then what if now the next one is time in seconds, and now time in minutes. Okay, time in minutes. What is my new function?
F of t over 60.
Y equal what?
F of t over 60. Divided by 60.
Right. F of t over 60. So that is the composition, right? Okay, now, and then when you differentiate, then y prime is equal to 1/60th f prime t over 60 by the chain rule. Okay. Similarly, y equal f of t, location in inches. Well, how about in feet? Okay, location in feet. Now I want location in inches. What is the function?
Y equals function of 12t.
That's right. That's right. 12 f of t. So you see the difference, right? It's once again a composition, and it is very simple composition because it's just multiplication. But in the former case, you do what? You first multiply. You take t, divide by 60, then apply f. Okay, that's the composition, consecutive computation. Here it is first you evaluate f, and then you divide, and then multiply by 12. But this one still, by the chain rule, still works. So it will be 12 f prime of t. I mean, it's actually not the chain rule necessarily, but the chain rule, as you can see, it actually includes in itself a lot of other properties. So I actually could have applied on right. I could have applied the constant multiple rule, and it turns out it is still applicable. The chain rule is still applicable, and suddenly it gives us the constant multiple rule. And then you can do both. You can do both, and you can have say y equal 12 f over t over 60. So your time was in seconds and location in feet, and then you decide time in minutes and location in inches, and that's your new function. And this is actually composition of three functions consecutively. Okay, so that might come up again, and then usually rescaling is just a linear, just a multiple, except for, well, can you think of any other examples when scale is not linear, not multiple? How about a shift? Celsius, Fahrenheit. There's a multiple there, but there is also a shift. The 0 of Celsius in Fahrenheit is not the same temperature. The feet, 0 feet, same as 0 inches, right? 0 seconds, 0 minutes is the same, unless you start counting at different time of the day. But Celsius and Fahrenheit, they're different. So 100, what is it? 0 degrees Celsius is 32 degrees Fahrenheit. Okay, so then you have to do a shift, and then once again, it's the composition. Okay, and there is a non-uniform D changes of variables, such as logarithmic scales. Have you heard of that? Logarithmic scales. Some things are measured in logarithmic scales, such as decibels and the Richter scale for earthquakes and so on. Well, anyway, we'll see a little bit of that probably later. But right now we're doing something different, and that is it's called implicit differentiation.
Is the Richter scale like 1 is 10, and then 2 is like 100?
Yeah, that's right. So that's the logarithmic exponential, as a matter of fact. So instead of adding, you're adding to the scale 1, but actually you multiply. That's exponential. For some reason, it's called logarithmic scale. Yeah, so like this. It's literally, it works like money in your bank. Okay, so implicit differentiation is, first of all, what is implicit? Implicit, we're going to be talking about implicit curves, because we now know how to find the tangent line to any graph. So this is a graph. Graph y equal f of x. If you give me a point on the graph, I can find a tangent line. Okay. So, but some of the curves, many curves in fact, are given implicitly. So let's start with that. So implicit curves, remember any? How about this one? What is this?
That circle?
It's a circle. So circle, radius 1, center at 0. Okay, what it makes it implicit, it creates a relation between x and y, but that relation exists only implicitly. So explicit, y equal x squared. Implicit, anything that not necessarily has been solved for y, or for x for that matter. So x squared plus y squared is equal to 1. It's not explicit. In fact, I could start explicit and I could write y minus x squared is equal to 0, and then suddenly the same thing becomes implicit. The problem with this circle is that it cannot be solved. Here I can go back from explicit to implicit very quickly, just solve for y equal x squared. But this one, if I try to solve for y, what do I get?
X squared minus 1 equals negative y squared.
Yeah, no, you got to say with y equal. So for y means that you explicitly express y in terms of x.
Y equals the negative square root of x squared minus 1, or 1 minus
1 minus x squared. But it is actually plus or minus. It could be negative. And so in other words, it is not unambiguous, because there are two possibilities, because it's not it does not satisfy the vertical line. What kind of circle is this? A little bit better. So it does not satisfy the vertical line test. Remember this one. Okay, so every time you'll get two possible answers when you solve for y. So in other words, you split it into two halves, and you could treat them separately and then solve whatever problem you want about it, including the tangent line. So it's not a problem in of itself, but it is a difficulty, and once you get more curves, you really don't want to do it necessarily that way. The other way is to actually treat it as an implicit relation. So instead, So what we're after tangent lines. So for tangent lines, so treat this, the x squared plus y squared equal 1 as an implicit relation, or rather implicit function. The relation is here, so that is a relation. This is our x squared plus y squared is equal to 1 is a relation between x and y, okay? But now we treat it as an implicit function. What it means that there is no, and there won't be, there is no y equals something. So just we throw it out. I mean, we have one equation. We don't want to do algebra with it necessarily in order to extract y or x. We could just deal with the way it is. X squared plus y squared is equal to 1. So in other words, that might sound weird at first. So there is no y equal anything in terms of x, but find y prime. Okay. So once again, there is no function explicitly, yet we want to find its derivative. So find the derivative of an unknown function. That certainly is not something that we have done so far. So we had an explicit formula. We plugged into the either limit definition of the derivative, or we use the rules of differentiation to get the function. But you have to start with the function that is given, okay, or at least the graph is given. And here we're not going to do that. We're going to do it implicitly. So what is the point? So how we differentiate the equation? Okay, differentiate the equation literally. So the equation is this, and we're gonna differentiate it. So let's first understand what it means. So first of all, what it means is that here y is an unknown function. Okay, y is an unknown function, and then what we have, then what our equation turns into is this: x squared plus y of x squared is equal to 1. Okay, so it's an equation of x. It's just there is a function there that has not been specified. Okay, and now that we're using this fact, I don't know, let's call it, I cannot call it a theorem, so I put it in quotation marks. So if two functions are equal, then their derivatives are also equal. So if, say, f of x is equal to g of x, then f prime of x is equal to g prime of x. So you see how the meaning of this theorem, it seems so obvious once you get used to this stuff. So sometimes it never comes up, but at the same time, sometimes it's a hurdle to understand the meaning of that. So if it's the same function, then of course it has the same derivative. It just sometimes in mathematics you state things that are so obvious that you just don't want to state them because they're just so obvious. If so that is just I guess it's just a weird way to state it in the way I did. If you put it in words as I did, if it is the same function, then it's the same derivative naturally. But if you imagine that there are two functions and they're equal to each other, then you conclude that their derivatives are also equal to each other. Whatever the point is, of course, is to applies primarily to what we're talking about, this equation that I'm about to differentiate, and we treat it as if we have two functions here. Okay, two functions in our equations. number 1 and number 2. So this is the important difference from all the equations that probably you have seen before, that this works for every x, and this is for every x, for every x. So the equations that you normally see in algebra is you have an equation of x, and you need to find what x is. There is one, maybe many x's, but you're supposed to find it. There is nothing to find here because the equation is supposed to, that's the assumption, that it is equal to, left-hand side is equal to the right-hand side for every value of x. So it is the same function. It is a very simple function on the right, just number 1. On the left, it's some function x squared. Well, it is parabola. The second function is not even known. We add them together, and then somehow they produce 1. But we don't know. That's the assumption that we start with. We have a function that just adds up to 1. How, and we don't know. But we do know that it is the same function on the left as it is on the right. Okay, and then according to this, then the derivatives will be also equal to each other. Okay? So let's try. So differentiate both. And they are equal. The results are equal. Let me make it clear. So x squared plus y of x squared prime is equal to 1 prime. Okay, you see what I did? So I started with that equation in the box, in the red box, two functions equal to each other. I differentiated both of them. The results are their derivatives. They're supposed to be equal to each other. Okay, so, well, that's all there is. The only difficulty is the fact that I have my unspecified function y there. But we'll figure it out. So let's start with the easy one. What's happening on the right?
Shouldn't it just be 1?
No. Derivative of 1? What? Derivative of 1?
Does that say that x equals 1?
No, it's a function. There is no x there, but it doesn't matter. We're looking at the right-hand side. It just happens to be a constant function, that's all. And the derivative is 0. Okay, so that just happens to be a constant function, that's all. Sometimes things are simpler, sometimes more complicated. If there is no x there, it's just good for us, it's easier, right? But it's still a function. Okay, now what's happening on the left? Let's start just little by little. So what would be my first step to do? What first rule to apply? The first rule to apply is the last operation that you carry out with the function. What's the last operation?
Sum rule?
Sum rule, yes, because the last operation is addition. Okay, so I'm applying the sum rule on left, and I have x squared prime plus yx squared prime. Okay? That so far so good. Now this one easy. X squared prime is 2x. Now this one is slightly more complicated. So what is this derivative? Well, what are we looking at?
It's got to be negative 2x.
Where is negative from?
I don't know, but it's got to equal that. 2x plus 1.
It's saying it has to equal 0.
No, that term that we need to differentiate. What is it? This thing. What is that? What are we looking at here? There's a function y that over x, and then there's a square. What are we talking about? Suppose you know how to compute hypothetically. Suppose you know how to compute the function y. Imagine how do you compute the whole thing. I'm giving you x. What do you do first?
Plug it in.
What?
Plug it in.
Yeah, okay, so, okay, what do I get from x? I get y of x. What do I do with y of x?
Square.
I squared. That's right. So y of x squared. So y, the first function. The second one is the square. It's another composition. It looks weird and maybe unusual, but really it is the composition of these two functions. One of them, the first one, is unspecified. But other than that, it's still just the composition. Y applied, you get y. Apply y to x, you get y. You remember that we talked about that sometimes the name of the function is the same as the name of the output variable, just to save on those letters. So that's exactly the case when y is the output, but at the same time it is the name of the function. Okay, so when we differentiate the composition, okay, we apply the chain rule. What do we get? This is the decomposition. So remember the chain rule. This is the chain rule, right? Remember what we do with it. The derivative of the composition is the product of the derivatives. So you just need to differentiate the two functions and then multiply. Okay, so let me on right. What should I do? What should I write here? Y is our function. What's the derivative? It's a trick question.
Would it be undefined?
Not undefined, it's unknown. It is what we're after. Remember, we're after tangent line. For the tangent line, we need to find the derivative. And, well, in fact, that it is a good news that y prime actually comes up. And then, and the second function is y squared. So when I differentiate, what do I get? I differentiated with respect to y, so I get 2y. Right? So y function, a function of x. So this is my differentiation, just like we did last week. Okay? Function y, I differentiate, I get y prime. Okay? Function, the second function is, say, z equal y squared. What do I get? I get 2y. Right? So what do I write here then? Can you see it? Yeah, that's mine.
2y.
What do I write here? By the chain rule, we have the two derivatives, so what do I have?
Y prime over 2y?
No, just multiply y prime times 2y. That's all. As far as differentiation is concerned, we're done with differentiation. The result, as you can see, this is by the way, I omitted the x, I omitted the x, 2x, but in fact, if I want to write it the way I did, it will be y prime of x times 2y of x equal to 0. So once again, y, we are treating y here is not as dependent variable, but we're treating as a function of x, the unknown function of x. And then on top of that, we have also the unknown derivative of that unknown function. Okay, and it seems like we have it all piled up here, but it's really not that bad because now I am after y prime. I am after y prime, so I just simply solve for y prime. Okay, so it is then equal to negative x over y. So as long as y is not equal to 0, this equation works fine. Okay, so as you can see, the answer is let me put y here like this. The answer is very much not what we're used to when we do differentiation. Why? Because there should be no y. When you have an explicit formula, y equal x squared, the derivative is also explicit, right? Y prime is equal to 2x. Explicit, there is no y on the right. That's explicit. And we have y. That is certainly, y kind of stands in the way, but it's really not that bad, because let's just use this formula. I want to use this formula to our advantage to find tangent lines. Remember, that's what we're after. So once again, if we have our circle, and we have and we suppose we are interested in some tangent line. So for example, I might be interested in the tangent line. How about this one? So suppose this is the tangent line. So what's the slope of this tangent line? Well, you know the answer, but let's see it in the formula. You see it in the formula. What's if you know the answer? Just give me the answer. What's the slope?
X equals 0 over 1, negative 0.
Right. So yeah. So you can see the picture seems 0. Okay, and then we can confirm it by looking at the formula. Because why? Because this is the point. This point over here. It is the point is 0, 1. So x equals 0, y equals 1. So indeed, if we substitute, what do we have? We have y prime of x is equal to negative 0 over 1, which is indeed 0. Okay. So the inconvenience of having y there is not a big deal, because if we do it one point at a time, we can always figure out what that y is. How? By just looking at by examination or by substitution if necessary. Y is an unspecified function, but we know what it is. So to see let's do one more. If I pick this point at 45 degrees, what is this point? So there is another slope, this one. Well, you probably can guess what the slope is. If not, let's plug in. So plug in what? X equal
Square root of 2.
yeah, that's right. Both of them are square root of 2 or 2.
It's 1.
So that's right. So you plug in and say y prime of x is equal to 1. So once again, it works out perfectly well every time. Every point x, y you pick on the circle will go through this computation, no problem. And even though, once again, we're finding the value of the derivative every time, even though we don't know neither what y is nor what y prime is. We'll find values every time we want. So I could pick this point. It will be, what is it? X equals square root of 2 over 2. Y is equal to, well, this is negative. I'm sorry. Yeah. Yeah, the negative sign. Y is equal to negative square root of 2 over 2, and then y prime of x is equal to 1. Okay, so this one, the other one is, this one has slope 1. Okay? So this is very typical problem. And it's, I'd say at its simplest, because simply because the graph is probably the most important implicit curve is the circle. Okay, so not only that, what we found the bunch of derivatives, but really typically, they remember those problems we looked at early on. It is we need to find the tangent line. So for example, if I am talking about the last one, the slope is 1. The point is, it's all here. This is the point slope. Okay, point slope. So if we have point and slope, we can write the equation, right? So give me the equation of the pink one by point slope formula.
X minus 1.
X no, why no.
The pink one?
Yeah. The point is the value of x at that location is square root of 2 over 2. So remember the point slope formula. y minus what? Y naught equal mx minus x naught. That's the point slope formula. And so we have m over here is equal to m, and then we have x naught, y naught over there. Okay? So then it will be y plus square root of 2 over 2 is equal to 1 x minus square root of 2 over 2. Okay? So that's the tangent line. Can you read it? Okay, that's not good color. Too pink. Okay, so that's how it works pretty much every time. So the only difference is the formula might be more complex. More complex than the circle. That's all. But the procedure is the same. The tricky, for a moment, tricky part of is the chain rule. Okay, so this is the tricky part right here. How to differentiate how to use the chain rule when one of the functions is unspecified. Not hard. You don't have to actually differentiate it. Remember, when you have two functions in the chain rule, you need both derivatives. And here you don't know one of the derivatives, which is fine. Then you just write y prime. Okay, that's all. So let's do one more. So volume of the card. So this is what the curve looks like. Well, roughly. It is actually slightly. It straightens out actually. Something like that. So the picture itself suggests that you can see how it appears to touch the x-axis as well as touch the y-axis. So that's the more trickier part, is when with the curve like that. Well, let me give you the equation. Is when you have they self-intersect. Okay, so that's the self-intersection, and then at the same location you have two possibilities, two different slopes. And in this particular case, it's especially inconvenient because there's one of them is vertical, which means that the slope won't work in the first place. But let's carry it out in a slightly more compact way. So I just go straight to differentiation. So the first time around is probably, it is better to do the way I did it over here, and then you have to remember that y is a function of x. So if you early on you don't put of x, the x in parentheses there, you might forget that y is a variable of x, and when you differentiate with respect to x, y is to be differentiated. So for example, y squared prime, it is not 2y, and it's not 0 either. Okay, so it appears that if you forget that y is not x, that is why the derivative is not 2y, but it's also not a constant, which means that the derivative is not equal to 0. It is in fact a function, unspecified function of x. Okay, so then I differentiate by the chain rule again, but first the sum rule here. So I have 3x squared. Okay, tell me what's the second term here is.
Y of x.
Yeah.
Cubed.
No, that's what I have. Y of x cubed. If I differentiate, what do I get?
Y prime times 3y.
3y squared. 3y squared times y prime, indeed. Okay, so as you can see, the first term is 3y squared as it would be if you're trying to differentiate with respect to y, which is something that you need to do anyway. Okay, but then because it is chain rule, that's the term that the term comes from the chain rule specifically. Okay, and on right, I apply the product rule, right? So I have, which means that I'll differentiate 6, 6, I'll take 6 out, and first I differentiate x, which gives me what? All differentiation with respect to x. So what's the derivative of x? 1, right? And then just simply, and then I leave y alone. Okay, so that's the first term. The second term, what's the second term? 6. Now I don't differentiate the first term x, so I simply keep x, and I multiply it by the derivative of what's left, y prime. Okay? 6y plus 6xy prime. So so I have to apply the chain rule twice. Well, it's not technically the chain rule, I suppose. It's just y prime, but as many times as y appears, you will have to, as many times y appears, as many times y prime will appear. Okay, so I have y appearing twice, so you have y prime appearing twice. Fortunately, every time it will appear as a multiple. And that's the good news, because it means that I can factor it out and solve for it. So this always works. Factor y prime out and solve for it. So in the last example, we did not have to worry about it because we had only one y present, and now we have 2. But at this point, it's just algebra. So I pull all y primes to the left and all the without y prime to the right. So I have 3y squared times y prime minus 6xy prime is equal to 6y minus 3x squared. Okay, so okay, now I factor out y prime, so I have y prime times 3y squared minus 6x, and still have 6y minus 3x squared. I probably should have divided by 3 early on, but I will do it later. Okay, so now just solve for y prime, so it will be 6y minus 3x squared, 3y squared minus 6x, or if I divide by 3, I have 2y minus x squared, y squared minus 2x. Okay? So whenever you have fractions, it is actually, even though it's kind of complicated, because once again you have x and y present at the same time, and you want to figure out what the slopes of this curve, even though the curve is actually, suppose we don't have the curve to refer to, so we have to actually use the formula to find those slopes. So, but whenever you have division, we have a fraction, you have the denominator, and there's a possibility that we're going to divide by 0. What does it tell us? What's the meaning of this equal to 0? So that undefined, which means the derivative is undefined. But it's not exactly right. There's a better way to put it. It means that in this particular case, we can be more specific. Remember those limits that we had, that some of them were non-existent and some of them were infinite. So divergent, but divergent to infinity. Yeah?
If the bottom one equals 0,
yeah,
the top one also equals 0, so it'll be 0 to 0?
No, it could be, but it doesn't. Is it? What you're saying is they are equal to. They could be equal to 0 simultaneously, but they don't have to technically. Okay, so I was just making that point is that actually it's a fair correction. So suppose this is not equal to 0, suppose, which is not actually accidentally it's not the case in this particular curve, but whenever the numerator is not equal to 0, denominator is equal to 0, then you can interpret this expression even not as a division by 0 undefined, but you can interpret it as infinity. Okay, so it is then indicate infinity, which, as far as the derivative is concerned, means that what does it say? Tell you about the tangent line? What does it tell you about the tangent line?
Doesn't mean it's straight and down.
It will be vertical. It will be vertical. In this particular case, it actually doesn't work out because if you look at the picture, you realize that there is a, well, I mean, it doesn't work out here, right? So because at this point both numerator and denominator are equal to 0, so that doesn't work out. It is exactly gives us 0 over 0, so that's a failure. But there is another point where this is the case. Y squared is equal to negative 2x. You see what I'm talking about? Y squared is equal to negative 2x. You see another point that satisfies this?
Negative x squared equals 2y on top.
No, I'm talking about this point. The slope is, the tangent line is vertical, right? So we can actually say what this is exactly. Well, we would have to plug it in, but into, that would be extra algebra. So find the point, but we do know that there is another one. Find this point. You'd have to actually find the value. This is the new equation is a parabola, right? It's a parabola that looks like this, so like this. So it intersects our curve, and at that intersection we have a vertical tangent line. And then we have also horizontal tangent line, right? Under what circumstances do we have a horizontal tangent line? That's easier. Equal to 0, not equal to 0. That's the horizontal tangent line. So as you can see, it's 2y is equal to minus x squared equal to 0. So that is, where is it? It's here somewhere. Okay. So as you can see, you can study the curve pretty extensively by looking at all the possibilities, and you pick any point, and you can find the tangent line in this manner. So we have found already one vertical, one horizontal. This one, the one in the middle, certainly has a challenge because the formula fails. Okay. Because you have it's not that you divide by 0, but you have 0 over 0, right? So at the origin, the problem at the origin is we have 0 over 0. Okay. So well, there are other techniques for solving this problem. These are all called implicit differentiation. In other words, for it is related rates. Related rates, it's pretty much the same. It's exactly the same setup, but explaining the words might take us slightly longer. If you look at this, these are related quantities. X and y. X and y are related to each other by an equation. Okay, and then they have their derivatives. They have their rates, and those rates are also related. Okay, so whatever we did here, we found the rates of x and y as they depend on each other. Specific problems are usually they're typically more like physics problem, and you have different, if you see a physics formula, you have a bunch of letters in them, right? And they are all different quantities. And the fact that we're used to having only two variables present is really not the case in any kind of application such as physics. So we have to learn how to sort that out. Anyway, we'll do that next time.